expert in the field, Meehan. Michael has a wealth of experience in high voltage asset management, and we are honored to have him with us today. Leveraging over 20 years of experience in high voltage asset management, Michael is a proven leader with a distinguished track record across diverse industry sectors. In his career, he has held progressively senior engineering and leadership positions, including roles at various industries. Currently, Michael is a general manager at Monitra, Australia. In his current capacity, he leads a team of experts focused on delivering best-in-class high-voltage asset management solutions. Throughout his career, he has fostered a deep understanding of high-voltage asset management across the entire asset life cycle. He is passionate about sharing his expertise and insight to help organizations achieve their high-voltage asset management goals. On behalf of IESWA chapter and everyone here, I would like to extend our heartfelt thanks to Michael for accepting our invitation and taking the time to share his expertise with us. Without further ado, please join me in welcoming Michael. Michael, the floor is yours. Thank you.
Thank you, Moed. When I wrote my spiel there, I didn't realise how that would sound when it came back. But no, thank you for the introduction. Pleasure to be presenting today. Big background on myself. Originally from the UK. Been in Australia for 12 plus years and have been working in and around the HV space for that time. Working in on and offline testing practices, and always learning, which is the key. Certainly wouldn't say I'm an expert. I think looking at who's in the call today, Mike Davies, who I did speak with briefly today, definitely call someone like Mike an expert. So my plan is to become someone who's someone like Mike, let's say. But yeah, just to begin, firstly, just to move that. Acknowledgement of country based on we are in Australia and I'm presenting from Perth today. So I would like to acknowledge and pay my respects to the Wodginook Nook people who are traditional custodians of the land in Perth, which I'm presenting from today. I pay respects to our elders, both past, present, and to the emerging leaders of the Noongar Nation. I acknowledge and respect their continuing connection to the land, waters, and culture, and the contribution they are making to life of this city and region. I extend that respect to other Aboriginal and Torres Strait Islanders who may be present today. So today's really some of the key points today is machines. What are their criticalities and what's the typical lifespan of a machine, and what might be some of the challenges in maintaining a machine in optimal life over the course of the needed operating requirements of asset owners, especially in this current day and age where we've got assets which are 20, 30 plus years of age and expected to run another 20, 30 plus years. So we need to be looking at how those assets can be kept in service for the foreseeable future, as well as new assets coming online, what can be adopted as best practice to sort of help maintain those assets. And PD testing, which we'll get into, is one method of ensuring that a machine is in its optimal condition for long service life. So just a bit on Monitra. So we are a UK-based business, but focus isn't on Monitra today, but we do specialize in sensors, in PD testing, and also software which helps support with PD testing, diagnostics, and trending of asset conditions to enable asset owners to make sensible decisions on maintenance interventions and when to make those calls on spending revenue on capex, opex. So we'll get into typical machine life expectancy. Typical machine operating life with a time-based overhaul approach would typically look like this, where you might have a overhaul halfway through its life. The machine will deteriorate through its operating life. Typical causes of that deterioration could be overloading, exceeding the machine's rated capacity can lead to overheating and therefore insulation breakdowns. Voltage imbalances, unequal voltages, distribution can cause increased current in certain phases, leading to overheating and component failure. Harmonics, distorted current waveforms can generate individual additional heating and stress on the machine. Starting and stop cycles, probably one of the most arduous. Frequent starts and stops can accelerate wear and tear on the components. Environmental conditions, exposure to extreme temperatures, humidity, contamination, or vibrations can also degrade the machine components. So based on these stresses the machine is exposed to in service, it is critical a maintenance strategy is put into place to maintain asset value to the operator and not rely on overhaul strategy. A periodic overhaul comprises of thorough inspections and repairs at intervals stipulated by the OEM, asset owner, or other driving factors that the owner-operator has. Potential issues with this approach is you end up having to do major work on the stator, potential rewinds, potential work on the rotor, and extensive downtime when you do need to do work because there's a fair bit to do. So to prevent having to have that approach, an implementation of a RCM strategy where you're starting to look at what potential failure modes might be impacting that particular asset in that environment in the way you operate it. So you'll start to look at how you can make them more visible and how you can start to make a proactive approach to how you tackle the long-term life of the asset. Some of those include visual inspections, which are fairly easy to do, looking for cracks, leaks in the footings or signs of overheating, vibration analysis, monitoring vibration levels to detect imbalances and bearing issues. Bentley Nevada systems are quite common and widely adopted in industry to sort of implement that strategy. RTDs obviously give the ability to look at your temperature profiles of your machine to make sure that you're not overheating or operating the machine beyond its operating parameters. Maybe additional cooling or some issues with the cooling system could be highlighted and repaired. Partial discharge systems. And now there's online solutions for that now, where you can take an online measurement, but not only that, you can have a permanent online system which will give you the ability to really correlate operating parameters with PD parameters and actually see the formation of PD maybe earlier due to the correlation of the other parameters, which is really what we will look at in some ways today. Obviously, bearing condition monitoring and alignment checks are other benefits of an RCM program, which basically turn that curve from being more downward sloping to more horizontal. And so if we think of the typical critical assets within a machine, we've got the condition versus stress. There's always stresses based on operating parameters, and there's a condition of the machine. Condition as new is everything's operating at will operate at desired parameters, and it'll continue to do so, all being well in an ideal world. But we know that stresses are in the ideal world, and not in the ideal world, sorry, which we live in, and those stresses do have an impact on the performance of the machine. So if we consider any component within the machine, could be the stator, the bearing, rotor, it will have a condition change based on stress. And as the condition potentially reduces and the stresses increases, you can end up with potential events which could cause potential failures. When a machine is new, an event such as inrush currents or surges from breakers switching, they may be tolerated by the machine initially, but over time, those events can lead to potential failure when the strength approaches the stress levels. There's a high risk of premature failure due to the transient, like you say, from those electrical surges or mechanical surges or other operating parameters which may exist. Contaminated winding left for too long, those sorts of things. The risk is greater when the machine does get old, which you approach end of life. So all of these factors obviously are in play, and when people are considering how to look at strategies to remove those stresses from the insulation. And there's a multitude of issues that could be, I'll go through just some, but turn to ground ratio create short circuits. This results in insulation breakdown, leading to increased current and overheating. Core damage through to vibrations, mechanical damage. There's rotor failures, rotor bar failures. I've seen this in a machine in the UK, bespoke machine. It was actually during a visual inspection, only 12 months into operation. It was a standard visual inspection. Nothing was expected to be seen during that visual inspection, and a good test engineer just happened to wipe his finger internally and had a white coating on his finger. Immediately that caused concern, and we took some further covers off, and that's when we found a broken rotor bar on the rotor, and that led to further investigations. And fundamentally, the rotor bar or the rotors were removed and replaced due to incorrect designing of the rotor bars themselves. Other issues, mechanical failures, shaft misalignments, coupling misalignments, all can be factors in lessening the motor's life of operation. So to remove that risk of premature motor failure and extend the end of life, which is the strategy of obviously the asset owners and engineers, we can introduce a condition assessment based program where we start to look at some of those key failure modes. And what we really want to try and do when we do that is identify how we can best track them, report them, trend them, correlate the information so it's not lost, and we start to piece things together. And when we do that, we can increase that trend line from being more downward facing to more horizontal, extending that end of life and removing the risk of premature failure. So as we get that advantage of extended life, we can do that through routine inspections. So I mentioned visual inspection earlier, some of the more simple and basic ones. Temperature monitoring we've mentioned, bearing condition monitoring, and all these are like routine offline type inspections. But what we want to try and do is go to a more preventative and condition-based approach. So some of the preventative options could be lubrication systems and analysis of the oils, filtering systems on those oils. So you start to become more preventative in your approach and less reactive and less time-based. And then we want to look at predictive as well. So that's where you do the you can do the MCSA for the HV machines, looking at your motor current signature analysis, which is an online condition monitoring tool for any potential rotor issues. PD now, as we mentioned, can provide that online PD detection system where if there is any issues, and there's a multitude of potential issues that PD can detect. And then obviously there's the vibration analysis system, which is also one of the key features, if not one of the most critical features of the generating unit itself. So by implementing these systems, we end up with two key advantages. We increase service life, we reduce the risk of in-service failures, which are costly to both operators and obviously the production process of a particular facility. In a hazardous area facility, obviously a failure of a HV machine could be catastrophic. If you're a power generator, obviously it could be a loss of revenue and significant penalties from any agreements in place in the networks. So the cost of these failures is fairly significant for most operators who have them. So in summary, we've identified that high voltage machines are prone to breakdowns and failures occur both electrical and mechanical wear and tear. In-service breakdown and failure, we say inevitable, but it is if you don't do any maintenance and you just expect the machine to run. Typically, the bigger the machine, the larger the stator, the longer the stator core, the more arduous the operation, the more condition monitoring or the more maintenance and attention to that maintenance practice is going to be needed. By using condition assessments and trending to detect incipient failure mechanisms and developing faults before they occur can help avoid these in-service failures, and you can plan for those preventative repairs. So when we think of the failure modes, this is a very common reference used, which is the team stresses. So if we think of these as individual failure modes effectively, which are attributed to as the clearly identified thermal. So temperature on a machine um, is one of the biggest and most common failure modes based on the insulation medium itself does not like to be put under extensive temperatures. It can become brittle. It can start to then crack. It then can start to contain moisture and start to reduce the insulation properties of the actual insulating medium. So temperature due to the copper losses I squared R and eddy currents, stray losses plus core losses lead to the insulation aging. Temperature plus air in air-cooled machines leads to oxidization, which means brittle insulation and potential delaminations. Thermomechanical stress due to load variations, copper expands more than the insulation, higher thermal expansion coefficients, and many load cycles, the adhesion may break. VSD, frequent short duration voltage lead to temperature tip-ups. They're all challenging and create these temperature issues within the machine. And stress, it does degrade the stress grading of the insulation, especially in VSD machines, if the VSD machine is maybe not designed or has issues during the design process. High temperature vaporizes moisture, reducing the risk of electrical tracking failures. So that's one advantage of maybe keeping the temperature right as well. So when the machine's offline, that's why you have the well, not sump heaters, but you've got the actual frame heaters just to keep that moisture out of the winding, especially when the machine's in a, let's say, coastal environment, an offshore environment. In general, you don't want the winding to become damp, and then obviously start it up. That can actually be a major problem. So just controlling the temperature while the winding or while the machine is offline is actually a very key feature of being able to maintain a healthy machine. The electrical stresses, so localized electrical stresses at the end winding section, there's a lot more stresses in that end winding region, potentially more vibration, depending if the end winding is being supported accordingly and sufficiently. Vibrations can lead to wear. When then up in that insulation wears, you end up with stresses, and that's when you can end up with PD activity and issues with the insulation. So PD is a symptom and not a cause of a failure. So obviously when we look at PD, we're not looking at the potential cause. PD is purely a symptom of a potential failure mode. So an end winding discharge, a contaminated winding, a loose wedge or surface tracking voids. So the PD can help with identifying the root cause, which is why PD is such a useful tool for looking after machines and being able to ensure that you've got that machine in a healthy state throughout its life. So we looked at ambient. So we look at ambient, we think of in the oil, moisture in the oil, obviously, plus dirt, local electrical stresses. You're going to end up with some issues if you don't maintain your bearings and that lubrication system in the right way. Some of the bearings, white metal, and the speeds and the heat that can be generated and everything else, the bearings themselves are probably the most critical feature of the machine, but there's well-established techniques to manage and maintain and monitor the condition of the bearings and the oil systems that are associated with those. The mechanical stresses. So we think of a machine, there is very strong magnetic forces that are involved with the stator and the way it interacts with obviously the rotor, and then you're turning some large, very heavy loads. So that the stresses in order to do that during startup, so regular startups, they do create these almost like magnetic shocks to the system. The common one is probably to think of when you think of a transformer being energized. You hear that hum in a machine. Not quite, you don't hear the hum necessarily, but you do get the sudden excitation of the stator and rotor and that jolt. It does cause those mechanical stresses. So it's important to factor in the load cycle of a machine. How often does it start? And realistically, a machine that starts a lot, you're probably going to want to have some extra awareness on better ways to reduce those starts, or at least look at ways to control the starts, soft starts, things like that. It's just to sort of remove those mechanical stresses from the machine. So when we think of a machine, obviously this is a very simple pictorial, but some of the key features and key areas of a machine that we look at where there's potential failure modes. Obviously state is one of the primary ones. I spoke about that quite a bit. You get the mechanical, you get those team stresses, which are quite prevalent across the stator. You do get cable box issues. It is a common, I've seen that quite a bit in the Pilbara in particular, where you get the differences in temperature. If the cable box itself is sealed, it can become, especially if there's a seal break between the stator housing and the cable box, you can get the heat from the machine going into the stator box. And maybe the machine then is switched off, and then you get these big temperature swings in the cable box, and you can end up with moisture in the cable box, which then leads to surface tracking. And I've seen quite a few cable failures in the Pilbara in transformer and cable boxes because of surface tracking and issues. So it is certainly a consideration when you are looking at your asset management plans for a HV machine, is how is that cable termination managed, and certainly make sure that you've got some visibility or some plans in place to make sure that it remains in a healthy state. The housing itself, obviously, it's important to keep the motor housing free from moisture, free from contamination, make sure all the seals are healthy. If the housing seals become compromised and all of a sudden you get dust, steam, other contaminants in and around the winding, obviously over time that contamination on the winding becomes a problem, and the winding itself will start to track, and you will start to get contaminants, which will then start to create failure modes on the winding. And you can pick this up in PD activity, surface tracking, the surface tracking PD patterns, which will correlate to contaminated windings. And there's a mining operator right now actually using data that were provided on contaminated winding, and now taking actions to do some dry ice cleaning and get that stator back to a more healthy state. So when we think of PD, obviously that's one of the key failure modes that we're looking at. In terms of what is the definition, it's always best to go off what the standards say, and obviously IEC have provided a nice definition for us, IEC 60270. So PD is a localized electrical discharge that only partially bridges the insulation between conductors, which can or cannot occur adjacent to a conductor. So it's important to reference partially bridged, because obviously when we testing, typically we're testing a healthy asset. And what we're seeing if we see PD is potentially that health degrading. So the PD activity, depending on the severity of the pulses, the accumulation of the pulses, all provide an indication of the type of problem that might be or might not be present in the machine. There's never a definitive time to failure with PD, but there is a more likely versus less likely type approach to when we provide the data, and when the analysis is complete. And based on the PD patterns, which we do touch on later, there is a strong correlation between certain patterns and definitive failure modes. And it's so well established now that obviously anyone who is provided a PD report with a particular failure mode present on a PD pattern, they will act upon it. But they'll be able to do that in such a time frame where they can probably wait for an outage or an appropriate window where there's less impact to production and operations. So the cost of any remedial actions is controlled. So when we think of failure modes and we talk about PD and stator and the other key elements of the machine, it's always good to correlate what's the likelihood. We're all based on risk, really. When we're engineering, the idea is we're in positions to reduce the likelihood of failure or manage the asset so it doesn't fail. So it's always on, and the production always runs, or the network always has its power. So to help with business cases and justifications for any condition monitoring strategy, we use global data, and EPRI and IEEE do provide, SEGRA do provide some as well, good information on potential failure modes and how prevalent they are within the industry, which helps asset owners understand where to invest their time and energy and what solutions might provide the best bang for buck and those sorts of things. So when we look at failure causes in the HV rotating machines, if we look at the top graph here, we can see that stator related, bearing related predominantly take up majority of the failure modes. Rotors are less common. I'm pretty sure this is on the 3.3 kV and above machines. Yep. So this is all high voltage machines that we're talking about. And of those failure causes from that top bar chart, the stator related ones, there's a further breakdown from those stator related failures into what the failure mode is. And stator winding insulation defects are PD related and will be caught during online monitoring spot testing. 75 to 90% of the stator related failure causes occur due to stator winding insulation failure. So obviously, when we're looking at insulation failure, typically it is a PD. You can detect that through the PD through PD testing. It's probably the most effective tool, and the reason that is the most effective tool is because you can do it while the machine's running. You're not having to wait for an outage event, do some offline testing. There's great advantages with tan delta and all the other testing, so it's definitely got its place and definitely a requirement to keep your machine healthy. But when you want to actually see the condition to make those business cases, you might have a requirement where the outage, you can't make it next month as planned, or in the next 6 months because of operational conditions you need to keep running. If you've got the ability to take some online measurements, you can be more confident that, yeah, we can push an outage out another 6 months, another 12 months, because we're not seeing anything that tells us otherwise. So it's all about getting that condition data, make it relevant, make it useful, so you've got these decisions that you can make these decisions with less of a finger in the air, and hope that nothing fails when you make those decisions. So it's a risk awareness, risk reduction type approach. So when we think of the way to develop the maintenance strategy plans, things that you want to look at, there's various input parameters which asset engineers are going to look at. These are probably the most common and critical input parameters. Obviously, you've got voltage rating. Higher the voltage, higher the stresses. 3.3 kV machine may not be as concerning or high cost as a, say, 11 kV generator, 15 kV generator, or compressor motor on a LNG facility. So when you do your asset management plans, there's a lot of factors that you take into consideration when you're looking at risk and planning what type of maintenance strategy best fits the motor, its machine, its environment, and everything else. And where you can, you want as much condition data as possible, on and offline. It all helps to correlate the motor condition. The preference to use offline is obviously a big advantage. Once you've got as much information as you can from the offline, you can then extend any offline outages by a year or two potentially. But mechanical wear and tear does happen, so the stator itself might remain really healthy condition, and then you've got the mechanical aspects to sort of juggle, and them are the challenges that come with machine management. So obviously, some of the benefits of monitoring the way we do is we minimize failures, we reduce that downtime, we do increase safety. there is some interesting. I think it was CS Energy. They had an interesting. I think the case study was just come out recently. I think it was CS Energy over East, where they had a machine which basically destroyed itself, and the motor housing went through the roof of the building and landed nearby. So when machines fail, they can be fairly catastrophic when they do. So there is certainly a safety component there that must be considered when you're looking at potential risks. But more often than not, it's a production loss or a economic loss, which is the biggest driver, and that's the most likely route that you're going to benefit from the most. And obviously extending the asset life, so you're not looking to do any major capex replacements. You can spend that money elsewhere. And keep the existing assets that you've got in operation for as long as you can. So when we think of PD, PD itself forms typically in voids. It forms across surfaces. It's a phenomenon which it used to be a bit of a dark art, and probably still is in some ways. And I think with technology, it's making PD now more accessible, I guess, to sort of the average engineer, and with the software and the sensors and the techniques used now, it's becoming more of a well-established tool. And standardization of analysis is important, and the way people now interpret results is becoming more consistent. I think a key thing to remember about PD, or a key point, is also to mention the difference between other assets. So if we think of a cable system or a switchboard, they'll be designed to be PD free. So you will look at 0 to 10 PC type tolerance levels when it comes to commissioning a switchboard or even a cable system. A machine is different. A machine is designed to be PD tolerant. And the installation, the VPI process, the way the machine is constructed, is designed to tolerate PD activity. So PD on a machine isn't per se bad, but there is PD activity which, when it forms, does indicate failure modes, and that is the type of activity that we want to be looking at and being able to interrogate, interpret, track, and trend, and then make decisions on. So this is where the technology that is now coming to the market is becoming better geared towards, let's say, it's with machine learning, which we'll touch on shortly. We can now start to look at how we can better correlate these PD patterns and then get better information to clients, and just better define issues. And with the way that we do that, we can start to look at not just patterns, but changes in patterns in a more definitive and finite way, by having that sensitivity of machine learning and computerization just being that bit more accurate than the human. But if we drill into what a typical void looks like, so potentially here we've got a typical PD pattern where we have a phase resolve pattern. It's important to reference the phase resolve pattern here, because any PD activity or any PD test for that matter, you really need to have that phase resolve pattern to be able to differentiate noise to PD. PD will occur based on the AC wave. It will charge, discharge the voids, and those voids will charge and discharge based on that AC cycle. So PD is predominantly an AC phenomenon. It's not a DC phenomenon. I believe there is some research happening on PD and HV in DC systems, but I think that's a fairly new field. From my understanding, most definitely it's a prevalent failure mode in AC systems, and the reason we use the phase resolve pattern, which is the PRBD system, is because we know that the PD does correlate with that. So whenever you see any PD reports, you will typically see this. You've got the AC, which is what we call our phase resolved, and you've got your positive and negative cycle. And PD activity will typically form patterns around that cycle, and from those patterns we can start to interpret potential failure modes. So here we've got a picture in the top left where you've got the insulation around the copper of the machine, and there's internal cavities of different shapes and dimensions around the ground wall insulation. So obviously you've got your insulation between your conductor and your frame or your ground wall, and these voids, even though they don't maybe look like to be too much of an issue, they will charge, they'll conduct, and over time you will get tracking, you will get a breakdown between the conductor and the ground wall, and that's when you do get the problems of a flashover, and potentially if it's a significant flashover, a potential rewind, or more, depending on the motor type. It could be a brand new motor based on the cost of repair. So delaminations are flat voids embedded in the insulation, particularly dangerous since the air interference decreases the thermal conductivity of the insulation, so it's trapped against the base of the machine, as it were. So you've got higher temperatures there, less air circulation, and you get these hot spots, and you get these potential issues in the winding. So the pattern and the distribution of the PD pulses determines the location of the voids inside the material or delamination from the conductor. So here we've got slot section discharges. So you can see there's a different pattern with the way that these PD occurs. So this is occurring between the HV, which is effectively the anode, and the metal, which is the cathode. So you've got the HV winding, and then you've got your frame. And basically you've got you've got a capacitance between the two, and you can start to get these charge buildups, and that's when you start to get these discharges. And if left, these will again turn into that issue between phase, between insulation, and the machine would fail in time. Again, there's never a definitive time to failure. But what we can say is the probability significantly increases when these types of PD patterns are observed. So when slot coating is too resistive or has been abraded by mechanical wear, such as from vibrations, you'll get asymmetric PD patterns, or predominant on one phase versus the other. So on this particular case, you can see on the negative half cycle of the PRPD pattern, you do get that buildup of PD. So just to explain the PD pattern here, the darker orange is severity of pulses, so number of pulses. So with PD, the way that we determine, there's a few different parameters that we look at, but in terms of the heat map, the number of pulses indicates the number of discharges, and obviously the more discharges, the more active a fault is. And then you've got the magnitude. So the left-hand side scale there is nanocoulombs. So that's energy. So obviously the larger the energy release, potentially the larger the void, which means potentially the bigger the issue could be. So when you get 10 nano to 20 nano, which would be fairly significant PD activity, and you start to get that heat map rise where you're getting severe pulse counts, your type of diagnosis there would be, there could be severe slot discharge or voids, and they could be fairly well advanced because of the energy that's being released. And this is the way that we start to look at PD patterns and how we can try to interpret them. And I'll get on to how we can use machine learning to make this whole process a little bit easier from a very quick level. So if we think of the state of core, we've got the end windings. The end windings particularly are tend to be quite a weak spot, I guess, in the way the motor is constructed. Just by in nature, the supports around the end windings are just not as good as obviously when they're in the slots and in the wedges and tightly compact. So the end windings do have to go through a lot of stresses. Obviously, we mentioned earlier about the arduous stop and starts of the machine. Those stops and starts create intense magnetic stresses, and those end windings can jolt, they can move. That movement can cause vibrations. It can loosen any potential supports, and over time, if they become too loose, they will rub, and they will potentially lose their integrity, and that's when you can get some severe issues at the end winding. The good thing is if you can pick a lot of these issues up early, you have the ability to do some repairs, in situ repairs, rebracing, apply some insulation, and basically get the machine back to that healthy state. So the whole point is to get that end of life extension to maintain that more horizontal condition profile as opposed to that downward facing profile. And then that way you're obviously doing the right thing by the machine. So if we think of there's surface discharges in this particular case study here. At the junction of the semiconductor of the stress gradient parts in end windings and overhangs. So the top left, you can see surface tracking. It's almost like carbonization, black sort of treeing, almost like roots spreading out from a tree or a plant. That's why they call it treeing, I guess. But really, that's looking to bridge the insulation. That's the high voltage stresses basically trying to find a way to ground or to stressing between conductors, and really, if left in that condition, that insulation would become a real issue, and you would end up with a failure mode in time. When the contact resistance between stress skating and slot coating is too large, or there is no contact at all. So these are some of the major issues with surface discharges. And yeah, some of the conductive pollutants that you would typically see in industry. Obviously, in the Pilbara, there's a lot of iron ore mines, and iron ore dust is, well, probably quite a good conductor, also not very good for the winding. Oil and gas, you might get oily environments, definitely heat and things like that affect the stress grading and do promote tracking, which is obviously something you want to avoid. So most HV machines can withstand these discharges for a long time. It's a bit like we said earlier, the insulation is designed to be PD tolerant. It's not a PD-free setup based on the way that the machine is configured and just by its design. So it is PD tolerant, but it's tolerant to a point. And obviously we need to monitor that point and make sure it doesn't get beyond it. These are some examples of what PD actually looks like in machines in terms of these are like from laboratory type pictures, but it just helps with that sort of visualization of how the PD from the windings from the stator itself tries to break the insulation between phases, between ground, and how it'll jump and track. So the picture here is clearly showing you the breakdown between the insulation in the stator core here, and then this is from an end winding, and this could be from vibrations that when the end winding comes out of its slot, that's one of the weak spots. And if you've got vibrations or the packing itself isn't quite what it needs to be, any movement there, you just need a bit of rubbing, and that bit of rubbing just degrades the insulation at that point, and then it starts to create PD, and then that can run away into a failure, which is obviously what you want to avoid. It's more after effects of potential issues. So this is a stator after in-service failure at the position where the slot sections meet the end winding. So you can see end winding again is always, well, not always, but it's a very high risk area in the way that the machine is constructed. There's some good and bad machine designs, and there's some very good ones out there, which mean that end winding discharges are not really an issue based on well manufactured and well built machines. And then there's other machines which maybe are not so well built, and you end up with these type issues. So it's definitely worth, if you are in a position where you're looking to buy critical HV machines, it's worth understanding how the machine is constructed, how it's actually made, and then when you're thinking of buying, it's like anything. If sometimes if you buy something that's a bit cheaper, it could be because the reliability of it might not be so good, but you need to know what things to look at. So it's certainly an area to sort of consider when you're looking at your machines in terms of future purchase or ongoing maintenance for sure. Visual inspections around the end winding, if you do have the opportunity while the machine's off, is very good. So yeah, certainly do that. Oops, go back one. There we go. It's just some more of the surface tracking and what the failing modes look like: contamination, poor stress control, inadequate clearances. You can see this all sorts of activity happening around this particular unwinding region, and yeah, just general surface tracking here, carbonized treeing. And yeah, it's the machine itself is a very mechanical in nature. However, when we test, we're using all these electrical properties to diagnose, but inevitably when we're looking at these electrical results, we're looking at mechanical type defects and failures. So being able to sort of link the two through these images is a good way of doing that. So in terms of how to implement a PD testing solution, we talk about measuring PD and we talk about testing, but what does it look like? Obviously, you've got a HV machine, it's high voltage. If we're talking about online in particular, how do you actually measure a high voltage system? How do you do that safely? Things like that. When it's offline, I'm not going to go into offline today, but there is test equipment where you'll apply a separate high voltage source, and you've got test equipment, obviously, that you'll hook up and do that measurement. And there's well-established practices on doing that, and it's still worthwhile. Very much one of the best things to do is to do them offline measurements, but you can't just do that every 4 years, 6 years, and think that's good enough. You do need to have the condition monitoring now to be able to have that extra condition visibility. And a way of having that extra visibility is to use data management systems and software. I just realized it's 10 to 6. So what we do is, well, I'll quickly skip to these sensors. So with the sensors that and these sensors are, we have what we think are quite unique sensors, but there is other sensors and technologies on the market, and they're all of a very similar nature. A high voltage coupling capacitor is exactly what it says. This will be fitted inside the motor terminal box. You've got the HT connection at the top here, which will be connected directly to UV and W. There'll be one per phase. That's how we get the phase resolve pattern. We're basically looking at PD from each phase as well. Sorry, that phase resolve pattern VSE, but we're looking at each phase, and that's how we get the ability to look at which phase potentially has issues based on time of flight measurements and correlation between PD patterns. High frequency CTs. We can also use these to detect PD, and they'll be connected to the cables at the cancelled screen region. And we've also got a patented way of measuring PD on VSD fed machines. Typically, a VSD fed machine wouldn't have a high voltage coupling capacitor, or potentially wouldn't, because of the transient pulses that are generated. So a way of measuring PD on a VSD machine in a safer way is to use a high frequency CT, so you're not directly coupled to the HV circuit and putting yourself in those transient voltage conditions. And you can then measure also with the TB3 the operating frequency of the machine, which gives you the ability to then look at if the machine's operating at, say, 30 hertz, then you can then do your phase resolve pattern at 30 hertz, and then you can still maintain that phase resolved analysis. Without the ability to detect the frequency of the VSD machine, you're just not able to do that PRPD analysis. Therefore, you can't do the PRPD or PD analysis on a VSD machine. So that is quite a useful tool, and we do use that a lot in oil and gas where there's a lot of VSD fed machines. If we think of the frequency response, or where the PD signals sit based on IEEE 60270, the frequency band that best determines PD activity in machine sits between 40 and 800 kilohertz. So the technology that you'll find on the market, typically the coupling capacitors are of these ranges. 500 PC we think is a very useful capacitance value. That's what we use, and obviously the high frequency CTs. And when we see here, you got your output response from your measurement units, and at 500 picofarads, we have very good high gain. So therefore, we can get some good sensitive measurements from PD activity in this whole frequency range. Similar to the high current HFCTs, we have a good frequency response throughout this current range. And it's important to be able to obviously have that sensitivity at 500 PC picofarads. We can see into the deeper into the winding and get that extra sensitivity. There is other frequency ranges which people use, non-IC, but still very useful, give you the benefit of seeing maybe deeper in the winding, and some people will test at 2 to 20 megahertz and also 20 to 200 megahertz. You will just see a significant drop off at that range. It's PD activity, just because you're looking deeper into the winding, you won't see anything as close to your measurement point, but it can be useful to be able to check at those frequency ranges just to help with any PD analysis and cross PD checks. In terms of what these installs look like, these are HFCTs on obviously the cable cores, and you can use this method obviously to detect the PD on a machine. This could be an at switchboard measurement solution. So we could measure PD potentially or we do measure PD from the switchboard to the machine. There's factors such as cable length, which we need to consider. Obviously, there's attenuation of signals and things. So we would need to assess cable size, core length, all those things before this could be an adopted solution, but it is a solution which we've adopted across a few client sites where at machine wasn't possible due to the cable box size. So when you're thinking of installing these coupling capacitors or HFCTs, some of the limitations might be if you're doing it post or after the fact, after it's been in operation for a while, you do have limitations in cable box sizes, potential limitations with cable access, cable screen configuration. So these are examples of perfect configurations, I guess, in terms of we're able to install these after the fact and give the client the condition monitoring that they require. The typical HFCT, HVCC hard voltage coupling capacitor install. We bespoke brackets, and then you've got the direct measurement from the machine itself. I'll quickly get into data acquisition and PD. So if you think of PD, PD isn't a constant. It does vary with humidity, temperature, load, and other parameters. And that's an important thing to remember. So if you think of PD here as the blue line, over time, obviously, that PD activity will change. It can trend if there's PD activity and it's degrading. Obviously, it'll trend upwards. Now, to be able to define that trend upwards, let's say, you would need to have a relatively frequent maintenance regime. So if we look at the red lines here, that would be a spot check, we would call it. So that could be every year, could be whatever frequency you can think of. But when you look at the difference in PD here to here, you might start to think, why is there less PD here? And then you test here, and then you've sort of confirmed, all right, this reading here is actually, this one was an anomaly. And then all of a sudden you test again, and now it's up here. So the point I'm making there is really PD does move around. You do need to look at those phase resolve patterns. There is other things you need to look at other than just PD magnitudes. And there is a science behind it. Continuous monitoring on critical assets like generators, or at least frequent testing, is of value because you can start to look at operating current, temperature, load, and you can start to see PD at certain frequencies, at certain times, at certain loads, at certain temperatures. You might have a normal frequency PD at that temperature, and you think, right, that's normal. And every time you get that temperature, the PD is similar, and it'll reduce at other temperatures, and then all of a sudden you've got what healthy looks like for that machine. So that's the real benefit of having that continuous monitoring, and you can start to then look at real changes based on correlations to temperature and other parameters and get that extra sensitivity in your measurements, which gives you the ability to make sensible management decisions on interventions if you think you need to make interventions. In terms of where the sensors are installed at machine, so hydro generator or generators and typical machines, HFCT example, and we've gone through the patterns in some ways. These are just more examples of the installs. This is what a system might look like in terms of you've got your acquisition, which is the grey box that links into the server of the client. You've obviously got all firewalls and everything else that obviously need to be in place now. I know for an oil and gas client just now, we've integrated an on-site solution for them, and we've gone through all of the IT hardening and other requirements that a system needs to go through to be able to be installed on a client's network. I'll maybe skip this and go into a little bit of the data analysis. So with the data analysis, we do have the what we call these heat maps, and the benefit of modern software now, some of this is quite unique to ourselves, but other clients and other OEMs do have software as well. But a key feature of the software is to be able to manipulate your analysis of the actual PD pulses. So we found the best way to identify PD patterns and PD problems is to really look at the individual pulses. We can do all of the usual IEEE 62700 frequency comparisons and look at PD as per the standards, but we also look at the amplitudes, frequency range, bandwidths, and we start to really look at the individual pulse and to see how that is forming, and then from that we can start to use so here we've got a phase resolve pattern, and we've gone through these in some ways, but I'll go skip to the way we analyze the pulses is quite key, and for anyone who is looking at PD analysis, it's important to be able to do the various clustering techniques and manipulating the data so you can actually look at the individual pulses. And by looking at the individual pulses, what we can actually do is create some machine learning rules, which is where we can define pulse shape characteristics, rise time, fall time, duration. So here, this would be, you'll see here, this would be a typical PD pulse. And you'll see this box here, that is that pulse. And obviously there's millions of these pulses throughout of this plot. Now, if you want to analyze each individual pulse, is it a pulse, is it noise, is it not noise, is it worth us taking it in consideration as a potential issue? This is key because this forms part of the mapping that you're going to use to then determine is there an end winding issue or not. So when we analyze these pulses, we can run machine learning on these million plus data points, remove any of which are not PD-like, and you could have noise which could be in some ways like PD, and we don't want that. So we don't want that to interfere with the way that we analyze and measure. So we can run machine learning on these vast data sets and end up with some very accurate and concise reports. And the big benefit there is when you do multiple tests, or you're looking at multiple data sets time after time, those rules that you set and that data that you're looking at, you get this real consistent and continuity in the way that things are analyzed. And you're removing that human error factor, and you're removing that maybe go-to person approach, which can be a problem because if that person's not available, you've lost your whole asset plan. So the benefit of going towards a more I guess, automated type PD analysis with there's still experts that look at this, but you get that consistency in analysis, and you still have the experts in the background working on this, but they're magnified in the way that they analyze because they can run a set of machine learning rules first, and they can then use their expertise at the back end and really focus on what they're looking at and spend less time just filtering through the noise. So there's a lot of benefits by doing it this way in terms of being able to get that more accurate PD plot and that PD analysis back to the client, who is obviously keen to know what is the condition of their asset. This is just some of the examples of how we would set up machine learning rules in our software. We define pulses, we interrogate that, we define that as what noise. Any other light pulses, we run that through the software. They would be removed. So here you can see there's VSD type pulses on this particular plot. When we go to the next, actually, sorry, I think there was a plot. I think I've missed it. But we can remove these switching pulses from our plots, and that gives us the ability to then give those final outcomes to the end user and asset owner. As it's 6 o'clock, I'm best off chat with you, Moed, and I realise people might want to dash off, but really this is just the dashboard. But I'll let you quickly interject, Moed.
Well, thank you, Michael. Yeah, it's 6 o'clock. It's very fabulous topic, and It was well presented. Thank you for that, Michael. I wish that we can have all the slides, but it could be we manage it in a way that we have it in 2 sessions, but unfortunately the timing is now it's 6 and some people they might to leave. If you don't mind, we just open for any questions from the audience.
Yeah, sure. Apologies. Yeah.
No, all good. Thank you. Thank you. It was fabulous. Very good and informative presentation. Thank you, Mike.
Hopefully everyone's still awake. Yeah.
Great. Anyone from the audience have question, please? I guess everything was clear. Mike, no questions. We have just Mike is typing on the chat, and
this will be too hard if it's coming from Mike Davies.
Yeah, Mike, ask hard questions, please. We have Obi asking if you can share the slides with them.
Oh yeah, for sure. Yeah, happy to. Yeah, I'll have to put it into PDF, obviously. But I can share the. Happy to share. Yeah.
No worries. Thank you. While Mike is typing, yeah, he just thanks for the presentation. A quick question. As per that, you mentioned that we have some the majority of the faults that in the generator. It's related to stator faults. Yes, we had some bearing faults, related faults as well, partial discharge. Can you just give some more detail on what could be when it's bearing related, and also the rotor related partial discharge? They were, if I remembered, only 10%. They were much less than the stator.
Also, sorry, I'll go back to this is the failure modes, wasn't it? So
yeah.
So I'll just maybe what I'll do is I'll bring up the slide, and maybe if you could repeat the question, that would be great. I think it was here, was it?
Yeah.
Is this what?
So we have we have 40%, which is quite high, bearing related partial discharge and faults. Yeah. Is that referring to the end of winding, or can you just give more detail on what could be the bearing related faults?
Bearing related. Oh, so this is to be honest, this is today I focused on stator. So everything we've discussed today really has been, so the stator related would be really what we're focused on, and all the PD related issues and everything else. With the bearing, that is purely obviously the mechanical, whether it's a pedestal bearing or the white metal bearing. You wouldn't, I'm not aware of picking up any PD activity from bearing related issues. I would say that would be a vibration and maybe a temperature of the bearing. So your condition monitoring of the bearings in terms of vibration sensors, temperature sensors, I think would be how that one is managed. Yeah.
Mm-hmm. No, great, thank you. And what about rotor? Yeah, as you said, you just focus on stator anyway.
Yeah, rotor related is obviously in a generator, not quite applicable, but on a typical squirrel cage motor, you can do the MCSA, which is very useful, and we've found. In fact, at the end of this presentation, I've got there is an MCSA case study where at the very end I'll find it here. So this is a very simple. It's actually real straightforward to do. Just going onto the CTs of the motor, clipping on using a clamp meter, and then you can look at these sidebands, and from these sidebands, if the sidebands are prominent, that can lead to the cracked rotor bar diagnosis. And we did this for an oil and gas operator out of Africa. It took some time for them to take this motor offline, but you can see clearly that there's quite significant sideband readings. And when they did take it offline, this is actually the end finding. The cracks. It's fairly significant. Yeah, I think if that was left in for much longer, it would have just destroyed the whole motor. Clearly, you can see here that they were starting to unlaminate, and there was activity that was starting to hit the end windings here. So this was I guess a good case study. The client would not have taken this out of service if we hadn't identified this. So it shows the importance really of doing the condition monitoring. Yeah.
Great, thank you. I'm not sure if we have any other questions. If not, we can end up to these sessions. Thank you so much again for presenting a very knowledgeable presentation. Thank you so much. Thanks everyone for joining. And yeah, you can find this on the YouTube channel. Thank you.
Yeah. Thanks, Moira. Appreciate the opportunity. And
Thank you.
Thanks. Hopefully people more than happy if you have questions afterwards, either flick Moed or look me up on LinkedIn, send me messages, and I'll try to answer them as best as I can. I look forward to catching you, Mike, if you're there next time you're in, maybe September, like you mentioned when we spoke earlier. That'll be good to catch up.
Thank you.
Thank you, Bud.
Bye.